that right there, this is a big thing. Like, why am I doing what I'm doing? Why does this matter? Okay, so whenever you take the quiz, why did I mark it round? Because you didn't show the resonance structure, because they actually matter. The three-dimensional shape of these
students
things.
need to report to lab 1110. Becca Hatfield, Paige Hatfield, Brady Lester, Joseph Morgan, Destiny Van Anna, Caitlin Wright. Go to 1110.
So in this, you guys, it matters behind what you're doing. I know this is a very, very basic level. I mean, this, honestly, in this class, you're just barely
I need to meet with
scratching.
junior sponsors this afternoon at 2:45 in the cafeteria. Thank you.
Just turn it off. Turn it down. At 2:45. The sponsors. Oh.
Because in this class, you're literally just scratching the surface of what chemistry is. But I want to make you aware, because for those of you that are like, I'm going to be a doctor, I'm going to be a pharmacist, I'm going to be a veterinarian, I'm going to do this, I'm going to go into the world of chemistry and change the world. You guys need to know what you're getting into, that this stuff does matter, and later on, your two-dimensional drawings that you're doing are going to change later on. So with that being said, here's my good friend sulfate. So let's work through sulfate. Sulfate is a very good example, because the first thing is some of you guys are catching on to this. Yes, sulfate is a rule breaker if it is being bonded with oxygen, chlorine, or fluorine. In this case, oxygen is being bonded to it, so sulfur can break the octet rule and form 6 bonds. Don't break it unless you have to. Alright? In this, which one is our center? Sulfur, oxygen?
Sulfur.
Sulfur. Why sulfur?
Because it has the least electronegativity.
Lowest electronegativity. Okay? There might have been a little confusion there when I gave you guys those rule breakers, because several of you guys have thrown this up in this class. Only hydrogen. Whenever I went over the rule breakers, it wasn't a blanket statement for all of them. Only hydrogen cannot be the center. So now we move to step 2 and we draw the skeleton. So at this point, I have 4 oxygen atoms, so now I'll draw 4 oxygens. With single bonds to the center, to the sulfur. Now in this, I give everything a full octet. Still stay with that. Just because you know sulfur is a rule breaker doesn't mean we're going to break the rule. So in this, we're going to give everything a full octet. At this time, you guys should be rolling and be fine and knowing that this oxygen needs 6 electrons. 2, 3, 6. Same thing for all of these. The reason you guys should see that they need 6 is these bonds count for 2. They want 8, so they need 6. If you are not getting that, feel free to come see me during lunch. First lunch, I'm in the auditorium until the freshmen leave the auditorium to go eat. Then I normally run down to teacher's lounge, use the restroom, and then I'm up here. So if you want to, you're more than welcome to come here, wait on me. You will see me. So in this, sulfur, do I need to add anything to the sulfur? The answer is no, because it has 1, 2, 3, 4 single bonds. Each bond counts as 2 electrons. So it has 8. So now we step to calculating how many of these electrons we actually got to show. And this is another thing, like walking around, I've seen you guys doing, that I want to make sure you guys are not messing up on. A lot of you guys automatically write your element down and you go 1. Don't just write the number 1 down. Look at the chemical formula. How many sulfurs do I have? In this case, yes, there is 1. Because there's not a number next to it, so I know there's 1 of them. So 1 times how many valence electrons does sulfur have? You look at your periodic table. Sulfur is in the 16th column, which means it has 6 valence electrons. 1 times 6 is 6. oxygen. How many oxygens do you have?
4.
You got 4. This is why you don't just write a number down. Look at it. Times the valence electrons that oxygen has. When you look at oxygen, it is in the 16th column, which means it has 6 valence electrons. 4 times 6?
24.
24. You're going to add those together. What gives you 30? And this is why Mr. Hall loves his polyatomic ions. Because a lot of you are going to stop right here and you're going to end up being wrong. Sulfate has an overall charge. This is where we account for that overall charge. This is the most simplistic way to do this for you. So in this, I have a -2 charge. So do I add 2 electrons or subtract 2 electrons?
Add.
I'm adding them because electrons are negatively charged subatomic particles. There are 2 negative charges up here, which means I add negative charges. So plus 2 gives me 32 electrons. So I have to show 32 electrons. No ifs, ands, or buts about it. I have to show 32. Let's count up what we're showing. 1, 2, 3, 4, 5, 6, 7, 8. Because these bonds count for 2. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Very nice. Are we finished?
No.
No, because we're showing 32, but what have we not done?
Charge.
Not check for charge. So now we got to check for charges. So in this case, we look at the number of valence electrons every one of these atoms start with and subtract how many valence electrons are being represented by it, and we split the bond. The bond only counts for 1 electron in this case. When we are checking charge and charge only. We're not checking the octet. So how many valence electrons for oxygen?
6.
So 6. How many valence electrons for sulfur?
6.
6. My voice just cracked. That was very funny. Alright, in this case, how many valence electrons does every one of these oxygens have?
7.
Okay, 7. Six minus 7 is -1. Oh wait, that was sulfur. Sorry, got carried away there. So every one of these oxygens, the way they are right now, have a negative charge. So we got to represent that negative charge. So now let's look at the sulfur. How many valence electrons is that sulfur showing?
4.
4. So 6 minus 4.
2.
So positive 2, so 2 positive. Then at this point, you all are going to do this thing. You're going to look and say, well, I have -4 and a positive 2, which gives me a -2. Those overall charges match. So I'm done. This is where life gets a little tricky. And this is the hardest of the hard. Because if you gave me that, you are wrong. Something that these molecules like to do. They love to keep symmetry, and they love to keep as little of a charge as possible. Is it possible for me to do away with charges here? Yes. Why is it possible for me to do away with these charges?
Because they can form 6 bonds.
It can form 6 bonds. When we're saying it, we're referring to sulfur. I know you knew that. I just want to make sure anybody watching the video knew that. So in this case, we're going to add in another bond. Where do you want to add it? Doesn't matter, you literally can just pick.
With yeah.
Okay, so we're going to add a double bond here. As soon as I do that, what must I do?
Take off the dots.
Take off the dots off the oxygen. I'm going to remove these two, and I'm doing that just because I want as much distance as possible. So in this case, do I remove any electrons off the sulfur?
No.
No. Reason we don't remove... Snack, that's the regular schedule. There we go. Goes to 1103. Okay, in this, we remove those dots, we don't remove off sulfur. Why? That's going to defeat the purpose that we're trying to do. We're breaking that octet, but we're allowed to break that octet on sulfur. So now in this case, look at the difference. How many valence electrons does oxygen normally have? 6. Minus how many is it showing now? 6. So, it's 0. That negative is no longer there. It is neutral now. Look at the sulfur. How many does it normally have? 6. Subtract out, how many does it have now? 5, which gives us positive 1 charge. So now that 2 goes away. We only have a single positive charge there. Is it possible for us to get rid of another charge?
Yep.
So we'll get rid of another charge. And this is where the other thing comes into play. Symmetry. For those of you that got this on your paper, I am not upset with you. But we are not going to put a double bond here or a double bond there. The reason we're not going to put a double bond in these spots is it would make these double bonds too close. We want symmetry. As symmetrical as we possibly can get. So our second double bond we're going to stick in right here. I stuck in a double bond, what do?
Get rid of it.
I get rid of a lone pair, so boom, boom, erase those electrons. Do I erase anything off the sulfur?
No.
No, because it would defeat the purpose. So in this case, we're looking at this. Oxygen normally starts with 6 valence electrons. Subtract out how many it's showing now?
6.
6, which is 0, makes it neutral, so now that negative charge is gone. What about the sulfur? Sulfur normally has 6, subtract out
6.
6, because it now is showing 6, it's neutral, so now that positive charge is gone. I did that to get rid of those charges. That's the whole premise behind what I just did. This is now more stable. So now, am I done?
No.
Why?
Resonance.
Resonance structure. These double bonds could have went here and here. So I must represent that in a resonance structure. So I give my resonance structure side. I build the skeleton. Now in this case, I change the position of where those double bonds are. Just so y'all don't watch the video and go, oh my gosh, where'd the double bond go? I don't see the blue. We'll put the double bonds there. Now in this case, we're going to add the electrons back in. If you want to sit there and count how many they need, you're more than welcome to, or if you just want to look at this as an example. But be careful. This oxygen that's sitting here is not going to get 2 lone pairs. This has a double bond. This does not. So the one with the double bond gets 2 lone pairs. And the oxygens that don't have the lone pair, they don't have the double bond, sorry, they get 3 lone pairs and a negative charge. For purpose so you can see it, negative, negative. Am I done?
I want to say yes.
I want to say yes also. Now, for those of you that are skeptic, you can absolutely go through and count these up, make sure it's showing 32
Teachers,
electrons.
we're going to have to change the bell schedule. It wasn't changed to the 3 hours, so you dismissed students on the wrong bell. We'll get that fixed right now.
On this, these are showing 32 electrons, which is what we want to do. That is our proper Lewis structure for sulfate. You have to show both of them. At this point, though, I don't want to leave here and go straight to the phosphite yet. I want to show you something. Because sulfate is a perfect example of this. So there is the 7 strong acids, and this is the backbone for the strongest of the 7 strong acids. It's called sulfuric acid. In this, sulfuric acid is literally, we add, if we're going to have an acid, it has hydrogen ions that it will protonate out. I do not care if you know what that means right now. I'm just trying to lay some foundation so you don't get caught off whenever I start using those words later on. So in this case, we have to have hydrogen.
Austin Gibson reports for Digital Learning Center, please. Austin Gibson.
We have to have hydrogen atoms along with this. The answer to how many, and this has helped foreshadow what we're going to be going on maybe start of next week. You look at the ions, so I have sulfate, SO4, 2 negative. You'll need the same number as the charge. So I need 2 hydrogens. And then that charge goes away. In this case, if I asked you to give me a Lewis structure of this acid, here's the key. Where would the hydrogens bond to? The negatives tell you where to go. So you have the same exact thing. And these negative charges that you see here tell you where those hydrogens will go for you. So you can kind of work backwards. You can do this, and then get this, and then say where the negatives are, hydrogens replace the negatives. So we take the negative off, and we add the hydrogens. But the hydrogens have to be bonded to the oxygen. So they will lose a lone pair to gain a bond and to gain a hydrogen. And that is now the properly drawn Lewis structures for sulfuric acid. Trying to link some things together for you. Here's the key. A nice little check for you guys when you're doing these polyatomic ions. If you have an overall charge, you are guaranteed to have to show an overall charge in your end result. The overall charges should add to equal that. This oxygen, sulfur, and oxygen are neutral. But these 2 oxygens have a -1 charge. So you have 2 -1s, that means you have a -2. Overall is 2 negative, therefore your charge is checked. It's a great, great, great way for you to check yourself. And remember, if you have the opportunity and you can work to get rid of one of those, of any charges within a molecule, get rid of it. Okay? How's everybody feeling? That one is the hardest of hard. Like, just being honest. Okay. I'm going to do phosphite, sorry. I'm going to work it a little fast. Just running out of time. Alright, so I have phosphite, I have PO3, 3 negative. So in this case, my center atom is going to be phosphorus because it has the lowest electronegativity. So I have phosphorus. Now I'm going to draw the skeleton out. This is being recorded, so you can go back and watch it later. So now in this case, I have the skeleton, phosphate's the center, I give everything a full octet. These oxygens on the outside need 3 lone pairs. And this phosphorus has 3 bonds, so it needs a lone pair as well. At this point, yes, phosphorus can break the octet. Is it a guarantee that phosphorus will break the octet? No. Not a guarantee. Now in this case, we've got to calculate up how many electrons we've got to show. So for phosphorus, I have 1 phosphorus. Phosphorus is in the 15th column, so it will have 5 valence electrons. So it's 1 times 5 is 5. Oxygen, I have 3 oxygens. 3 times 6, that is 16. 18, sorry. Seen the 6, got caught on the 6. 3 times 6 is 18. Now in this case, how many electrons I got? I have an overall charge of 3. So I'm going to add those 3 along with that. So in this case, what's 5 plus 18 plus 3?
26.
Thank you, 26. So I got 26 electrons I have to show. So 26 is my number. I count it up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Bada boom, bada bing. Let's look at charge. In this case, these oxygens, all of them start off with 6 valence electrons. I know I'm moving quick. You guys should be catching up quicker to this than what you're used to. Look at phosphorus. Phosphorus normally has how many?
12.
Good job. So in this case, how much are the oxygens showing? 7. Here. I got a hammer drill. So in this case, every one of them has a -1 charge. How many is the phosphorus showing? 5. So it's neutral. So in this case, all of them get negative charges, and all of the phosphorus is neutral. So, does this work out?
Maybe.
What's the overall charge supposed to be?
-3.
-3. What's the charge that we got?
-3.
-3. Can we get rid of any charges?
You can, but do you have to?
If I got rid of a charge, I'd add a charge. It'd kind of be like this whole playing around kind of thing.
Nah, it just doesn't seem like the aberration.
Yeah, that's exactly why we shouldn't worry about that. You guys are good. Just listen to me. You want your practice sheet now, or you want it tomorrow? Okay, listen. I know these last ones can be a little hard, all right? I'm also going to look at you and tell you I will have a gift for you. Matter of fact, we're going to have 2 gifts. I know, it's very exciting.
Is one of them a periodic table?
ions involved, there's an opportunity for some points.
Ooh. Exciting. I'm serious.
Her definition of ooh is going to change in a second. I will also be giving you a list of polyatomic ions. Y'all remember that element quiz you guys took? It went very well for you guys. I was very pleased, very happy. So guess what you will be having coming up? A polyatomic ion quiz. I'm telling you and forewarning you now, the polyatomic ion quiz is more difficult. But I'm also the person that's going to look at you and tell you, you also have a normal quiz coming up.
Oh my God. You were just on a roll with that.
I know, right? Ain't you so happy?
Told you.
Do what?
So, tell this second about the element quiz that I made a good grade on.
We're on live grade.
I
What?
told you because
What is your
you
question?
got our hopes up.
I'm saying, so if I fail this one, it's going to just like knock out my element quiz I made a good grade on. It's gonna bring
But you're not
me
going to
right
fail
back.
it. You're going to study and do great.
Mr. Hall,
Remember,
I'm not
with your
wrong.
normal quiz, once you learn it, all is fair game. Which means I can ask you any question of anything I've taught you.
Oh, don't do
Why
that.
would you do that?
That makes
Because all is fair game. The reason why is because when you get to college, that's how professors are, and I want to prepare you now instead of later.
It's okay, you don't have to prepare us.
No, I do. Because when you look, I'm sick and tired of kids that want to be doctors and pharmacists and stuff, and they go and they can't even pass their first chemistry class. So I made a promise to myself. I turned this class into what it really should be, and I will not back down from it. You can do this. I'm forewarning you. I'm telling you. It's not like I'm looking at you and telling you that this Friday is your quiz, because it's not. Your normal quiz will be next Friday. Before y'all freak, your physics quiz got moved, which you already know because you messaged me.
Yeah.
Your polyatomic ion quiz will be one day next week before the regular quiz. I will get you the list tomorrow so you can start making your flashcards and start studying. Besides that, get that out of my face. Go crush your second period.
Go crush some art class.